Hi, this is a presentation on our paper called Triplet Interaction Improves Graph Transformers, Accurate Molecular Graph Learning with Triplet Graph Transformers. So let's begin with some background on graph transformers. Graph transformers have two important advantages over graph convolutional neural networks. One, they allow long-range interactions, meaning that any node can aggregate any other node in a single step. And two, these interactions are dynamic, meaning that the network decides the weights of these interactions depending on the input graph. However, graph transformers use handcrafted positional encodings or features, limiting their geometric or structural understanding to the input graph. This is true for simple graph transformers like graphormer and geometric transformers like equiformer. However, in the spirit of deep representation learning, we want to let the network form its own deeper representations of the graph topology. This is where pair representations help us. Pair representations EIJ are assigned to all pairs IJ, regardless of whether they are connected or not. Similar to the node representations HI, they are updated in each layer. This allows for the topology of the graph to evolve over layers, potentially breaking free from the inaccuracies in the input graph topology. Additionally, any pair-related tasks like link prediction, edge classification, or distance prediction can be performed directly from these pair embeddings. These were introduced in our previous work, the edge-augmented graph transformer, which allows the network to break free of the input graph topology by making tuples first-class citizens, just like nodes. However, EGT uses only second-order interactions, and as we will see, this limits its understanding of geometric graphs. Geometric graphs represent points in space as nodes, and their relative positions as edges. One very common use case can be found in 3D molecular geometry. Molecules can be expressed as either as atoms and the bonds between them, which we call the 2D graph, or as atoms and their 3D coordinates, which we call the 3D graph. However, the interatomic distances can be used to represent the 3D graph in a coordinate-free manner. Although 2D graph annotations are more easily available for chemical species, the 3D coordinates of the atoms are also very important and directly dictate their properties. However, true 3D geometry is computationally expensive to obtain, requiring quantum mechanical simulations. In order to bridge this gap, we want to train a deep learning model on 2D graphs to predict the 3D geometry of the molecules. However, this task requires improving the geometric understanding of our model. It can be shown that the understanding of different geometric features is directly related to the order of the interactions within a model. We can either manually incorporate these features or design a more expressive model with higher-order interactions, which can infer these features. Second-order interactions within tuples only allow for understanding of pairwise distances, while third-order interactions within a 3-tuple IJK can allow for understanding of angles, area of triangles. Similarly, dihedral angles requires fourth-order interactions within a 4-tuple, but this would be computationally too expensive. In this work, we introduce third-order triplet interactions, which take place among adjacent pairs, IJ, JK, and IK, within a 3-tuple IJK. So why do we resort to third-order interactions rather than using third-order features like angles directly? We have to remember that these features are derived from the input geometry. So if we do not have a good input estimation, we cannot predict the true geometry. This means that we will always need an initial estimation. On the other hand, using third-order interactions allows use a simple graph as input while directly predicting the geometry from scratch, no initial estimation required. Secondly, using features derived from the input geometry would mean that the understanding of the network would only be as accurate as the input geometry. However, using triplet interactions allows the network to break free from the input geometry and learn more accurate representations. Lastly, geometric GNNs use such features to predict molecular properties, but their usage is thus limited to geometric graphs only. Since triplet interactions can be used on any graph, we improve the geometric understanding of the network without losing any generality. It can be used for both graph representation learning and geometric deep learning. Now, let's delve into our main contribution, the triplet graph transformer. incorporating a novel triplet interaction mechanism to improve the geometric understanding of graph transformers, which is particularly beneficial for tasks involving molecular graphs. Let's examine the triplet interaction within a three-tuple IJK. This is the core mechanism that allows our triplet graph transformer to capture third-order geometric relationships. In the inward update, we have three participants, IJ, JK, and IK. The key idea is that the pair IJ gathers information from JK. However, the way this information flows is crucial. Without triplet interaction, the information would flow from JK to node J, and then to IJ. This creates a bottleneck at node J, limiting the expressivity of the model. With our triplet interaction, we enable direct communication. JK can directly update IJ. Moreover, IK also participates in this process, allowing for a more comprehensive update that considers all pairwise relationships within the three-tuple. We also have an outward update that works similarly, but in the opposite direction. We've developed two mechanisms to implement this interaction, each with its own strengths. The first mechanism is triplet attention, which we call TGT-AT. In this approach, we compute the inward update for the pair, IJ, using the equation shown here. The attention weight AIJK is determined by a combination of dot product attention and a gating term. This mechanism is highly expressive, allowing for complex interactions between the pairs, but it comes at a computational cost of ON cubed. Our second mechanism is triplet aggregation, or TGT-AG. This is a more efficient alternative that sacrifices some expressivity for speed. The key difference here is that we remove the dependence on the junction node J in the weight calculation. This allows us to use tensor multiplication, reducing the computational complexity to approximately ON to the 2.37. In our previous work, EGT, we introduced a two-track model with two types of representations: node representations, which are processed through node channels, and pair representations, which are processed through edge channels. TGT builds upon this foundation, but introduces a crucial improvement in the form of a triplet interaction module, which updates pair representations based on each other, enabling third-order interactions. Looking at the diagram on the right, you can see that the node and edge channels go through an EGT attention layer responsible for updating both using a second-order attention mechanism. But then we introduce the new triplet interaction layer. This allows pair representations to directly influence each other, capturing more complex geometric relationships. One of the most powerful aspects of this architecture is that the pair embeddings can be directly used for predicting pairwise atomic distances. It's worth noting that while we developed this architecture with molecular graphs in mind, it's actually quite versatile. We found it to be useful for other geometric tasks as well. For example, it performs well on the traveling salesman problem, which is a graph learning problem on the 2D plane. Let's discuss our model architecture and training methodology. Our approach revolves around two cascading TGT models, a distance predictor and the task predictor. Training consists of three main stages. In stage 1, we train our distance predictor. This model takes a 2D molecular graph as input, along with an optional initial distance estimate. It is trained to predict interatomic distances, which are output as binned values. Moving on to stage 2, we pre-train our task predictor. Here, we introduce some noise to the ground truth 3D structures. This noisy distance information, along with the 2D graph, is fed into the task pred. The model is trained to predict the target property, while also maintaining a secondary objective of predicting the ground truth binned distances. This dual objective helps in regularization and ensures that the model doesn't overfit. Stage 3 is where we fine-tune our task predictor on predicted distances. We use the dist pred from stage 1 to generate distance predictions, which are then fed into the task pred along with the 2D graph. The task pred is fine-tuned to predict the target property, while still maintaining the distance prediction objective for regularization. During inference, we employ a stochastic approach. The dist pred generates multiple distance predictions, which are then passed through the task pred, that is, dropout is kept on. This allows us to make multiple sample predictions and estimate uncertainty, which is particularly valuable in applications like drug discovery and material design. This two-stage model architecture, combined with our three-stage training approach and stochastic inference strategy, enables us to make fast, accurate, and robust predictions of target properties from 2D graph inputs. Now let's discuss some additional contributions of our work that enhance the performance and robustness of our model. First, we introduce a locally smoothed 3D noise for pre-training the task predictor. This is represented by the equation you see here. Essentially, we're adding noise to the 3D coordinates of each atom, but in a way that preserves local geometric relationships. The noise for each atom is influenced by its neighbors, with the influence decaying exponentially with distance. This approach helps our model learn to be robust to small perturbations in atomic positions, which is crucial when dealing with predicted geometries that may not be perfectly accurate. Locally smoothed 3D noise better mimics real-world scenarios, where atoms that are close together tend to move together, while those that are far apart can move more independently. Our second contribution is a novel regularization technique for graph transformers called source dropout. This is a stronger form of regularization compared to traditional attention dropout, which is commonly used in transformer architectures. In attention dropout, individual attention weights are randomly set to 0. However, in our source dropout method, we drop entire columns of key-value pairs for all queries in all heads within a layer. The figure illustrates the difference between these two approaches. On the left, you see attention dropout, where individual cells are randomly dropped. On the right, you see our source dropout, where entire columns are dropped consistently across all attention heads. The effect of source dropout is to make some nodes invisible to others during the information exchange process. This forces the model to learn more robust representations that can handle missing information. To reiterate, let's summarize the key contributions of our work. First and foremost, we introduced the Triplet Graph Transformer, or TGT. This is our main architectural innovation, featuring novel triplet interaction mechanisms that enable direct pair-to-pair communication within the model. This approach allows TGT to accurately model geometry in graphs, which is crucial for tasks involving molecular structures. Secondly, we present a two-stage model design. This consists of separate distance and task predictors. The beauty of this approach is that it eliminates the need for initial 3D coordinates, allowing us to work directly with 2D molecular graphs. Our third major contribution is the three-stage training procedure coupled with stochastic inference. This methodology significantly improves both training efficiency and predictive performance. It allows us to make robust predictions even when dealing with uncertain or noisy input data. Lastly, we demonstrate the versatility of TGT beyond molecular graphs. We show its effectiveness in general graph learning tasks, specifically highlighting its performance on the traveling salesman problem. This illustrates that our approach can be valuable in a wide range of applications involving geometric relationships in graph-structured data. Now let's dive into the results for large-scale quantum chemistry tasks. The key challenge here is to predict properties in the absence of ground truth 3D structures, which is a significant leap forward in computational efficiency. We've tested our models on two important datasets, PCQM4Mv2 for molecules and OC20 IS2RE for crystals. Our TGT model is currently the top-performing model on the public leaderboards for both of these datasets. Looking at the PCQM4Mv2 results, we can see a clear progression in performance. Our TGT-AT model, especially when combined with initial RD-kit coordinates, achieves the best performance with an MAE of 68.3 millielectron-volt. This is a substantial improvement over the previous state-of-the-art Unimol Plus model. It's worth noting that our TGT-AT model performs well, even without the RD-kit initial estimate. The previous best model, Transformer M, falls far short in this scenario. This result showcases the power of our triplet interaction mechanism in capturing complex geometric relationships, even when working solely with 2D graph inputs. Moving on to the OC20 dataset for crystal structures, we see similarly impressive results. Our TGT-AT model achieves an MAE very close to Unimol Plus. However, when we look at the energy within threshold EWT metric, our TGT-AT model slightly outperforms Unimol Plus. Also, not shown here, when we break down the performance on out-of-distribution catalyst adsorbate systems, TGT actually outperforms other models. Now, let's move on to a different setup where the ground truth 3D structure is provided, so we don't need to use our distance predictor. We're only fine-tuning the task predictor, which was pre-trained on the PCQM4Mv2 dataset. We're focusing on the QM9 dataset, a benchmark dataset for molecules. Looking at the results, we can see that our TGT-AG model performs exceptionally well. It achieves the best results on 5 out of the 7 tasks and performs competitively on the other 2. Notably, our model shows outstanding performance on HOMO, LUMO, and the HOMO-LUMO gap. This exceptional performance can be attributed to the fact that our pre-training dataset, PCQM4Mv2, specifically targets the HOMO-LUMO gap, allowing our model to develop a deep understanding of these electronic properties. It's important to highlight that TGT-AG outperforms the previous generalist model, Transformer M, across the board. Even more impressively, it surpasses specialized geometric GNNs and transformers in most cases. This demonstrates that our model has developed an enhanced geometric understanding, despite being designed as a more general-purpose architecture. Moving on to non-quantum property prediction and drug discovery tasks. Here we use our distance predictor that was trained on PCQM4Mv2. A key point here is that we're using a frozen distance predictor. It's not fine-tuned on these new tasks. For MOLPCBA, our TGT-AG model with the distance predictor, TGT-AG plus DP, achieves the best performance with an average precision of 31.67%. This outperforms both the previous state-of-the-art Graphformer model and our own TGT-AG model when using RD-Kit coordinates. For LIT-PCBA, we're using ROC-AUC as our metric. Here, our EGT model with the distance predictor, EGT plus DP, matches the performance of the current best model, GEM-TUPS RD-Kit. These results demonstrate that the 3D information from our distance predictor, which was trained on DFT calculated coordinates, appears to be more useful than the information provided by RD-Kit coordinates. Now, let's shift gears and look at how our model performs on a classic graph learning problem, the traveling salesman problem, or TSP. In this setup, we're dealing with points on a 2D plane, and our task is edge classification, determining which edges should be part of the optimal tour. Looking at the results table, the baseline GNN gated GCN achieves an F1 score of 83.8%. ARGNP, a more recent model, improves on this with 85.5%. Our previous work, EGT, performs similarly. However, our new TGT-AG-X4 model significantly outperforms these with an F1 score of 87.1%. This is a substantial improvement over the previous state-of-the-art. The X4 indicates that we're using 4 repeated layers with shared parameters. These results demonstrate the generality of our model. Let's discuss the merits of stochastic inference. On the left, we see how performance varies with the number of samples. With just about 4 samples, our stochastic inference outperforms the deterministic MAE, indicated by the dotted blue line. This demonstrates that even with a small number of samples, we can achieve better results than a single deterministic prediction. Moving to the right graph, we see how performance relates to confidence. As we increase the confidence threshold, the MAE decreases significantly while the EWT increases. This tells us that when our model is more confident in its predictions, it tends to be more accurate. This stochastic approach is particularly valuable in fields like drug discovery and material design, where understanding the uncertainty of predictions can be just as important as the predictions themselves. As we conclude, let's look at some directions for future work. First, we want to explore the use of triplet interaction for a wider range of graph learning tasks, including molecule and conformation generation, which could have significant implications for drug discovery. We also see potential in link prediction tasks, other combinatorial problems beyond TSP, as well as in self-supervised, semi-supervised, and generative graph learning paradigms. Secondly, while triplet interaction is already proven effective, reducing its computational and memory requirements would make it even more practical for large-scale applications. We're particularly interested in exploring applying sparsity and linearity to the triplet interaction mechanism to achieve this goal. Thank you all for your attention. This concludes my presentation. For those interested in a deeper dive into our research, I encourage you to check out our paper for more detailed information.